Welcome to 1.4. We're talking about composition of functions. Our learning outcomes for this section are combine functions using algebraic expressions, create new functions by composition of functions, evaluate composition of functions, find the domain of a composite function, and decompose a composite function into its component functions. So in this part, we're going to be looking at the combining functions portion. So combining functions using algebraic operations. For two functions f of x and g of x with real number outputs, we define new functions f plus g, f minus g, f times g, and f divided by g by the relations f plus g of x is f of x plus g of x. F minus g of x is f of x minus g of x. F times g of x is f of x times g of x. And f divided by g of x is f of x divided by g of x. So for example 1, find and simplify f times g of x and f minus g of x, f minus g quantity of x, for f of x being x minus 1 and g of x being x squared minus 1. So for f times g of x, that's going to be f of x times g of x, which is x minus 1 times x squared minus 1. We could just FOIL this out. So x cubed minus x squared plus 1, or x cubed x cubed minus x squared minus x minus 1. If you've been watching my videos, it's some reason defaults in black when I start. But then when I just went back from erasing, it went to the blue, so interesting. F minus g of x. I like blue because it gives it some vibrancy and color, and it looks less like a photocopy, but whatever. Either one works. So we have x minus 1 minus the quantity x squared minus 1. So it's x minus 1 minus x squared plus 1. From that, the 1's go away. And we have either x minus x squared or negative x squared plus x. Either one. I mean, if you want descending order, do the negative x squared plus x. So a composition of functions, I have a definition here. When the output of one function is used as the input of the other, we call the entire operation a composition of functions. For any input x and functions f and g, this action defines a composite function. Think of composite, something's made of something else, which we write as f of g. This is not times, it means f of g of x. That means the function f composed of g of x. So you evaluate your g of x first, and what that outputs is what is plugged into the f as input. So the domain of the composite function f of g is all x such that x is in the domain of g and g of x, so the output is in the domain of f. It's important to realize that the production of functions f times g is not the same as the function composition f of g of x, because f times g, f of x times g of x is not f of g of x, so these are two different things. So using the functions, find f of g of x and g of f of x, determine whether the composition of the functions is commutative. So our f of g of x means that this should be, there should be an equal sign. Sorry about that. In fact, let me just fix that now. There we go. So this 4 minus x goes in place of the g of x. That's what the output is. So this is f of 4 minus x. So 4 minus x gets put in place of this x in the f function. So it's 3 times 4 minus x minus 1. So I get 12 minus 3x minus 1, or 11 minus 3x. For my g of f of x, That's going to be g of the function 3x minus 1. That's a minus 1. So that's going to be 4 minus 3x minus 1, because g is just 4 minus x, so the 3x minus 1 is replacing that x. So that's going to be 4 minus 3x plus 1, or 5 minus 3x, or negative 3x plus 5, which clearly these are not the same thing. These are not the same. So the point is, as a rule, the composition of functions is not commutative. If it is commutative, there are some fun cases where you get the same answer, but that's very rare. I mean, it would happen in an infinite number of cases, but it's not very common. Okay. The function c of s gives us the number of calories burned by completing s sit-ups, and s of t gives the number of sit-ups a person can complete in t minutes. So interpret c of s of 5. So s of 5 is sit-ups in 5 minutes. So c of s of 5 is calories burned by doing sit-ups for 5 minutes. Example 4. Suppose f of x gives miles that can be driven in x hours, and g of y gives the gallons of gas used in driving y miles. So which of these expressions is meaningful? F of g of y or g of f of x? Well, what do you think? F of g of y would be miles driven per, well, that's not even going to work, because the input for f is hours, but g is not producing hours, it's producing gallons. But the output for f is miles, and the input for g is miles. So this would be more meaningful, because so we get hours gives us miles, and the miles gives us gallons. So g of f of x is meaningful. Because the output for f is the input for g. Okay, let's do another one. Use the table to evaluate f of g of 1 and g of f of 4. So what is our g of 1? So if x is 1, g of 1 is 3. So that's 3. So f of g of 1 is f of 3, because g of 1 is 3, and f of 3 is 3. And then g of f of 4 is what? Because f of 4, so look at 4, that's going to be 1, is 1. So this is going to be g of 1. Oh, we already know that one from before, which is 3. Okay, that's it there. And we'll look at evaluating a composite function given its graph. So locate the given input to the inner function on the x-axis of its graph. Read off the output of the inner function from the y-axis. Locate the inner function output on the x-axis of the graph of the other function. Read the output of the outer function from the y-axis of its graph. This is the output of the composite function. So, for example, f of g of 5. So we look for G of 5. Here's 5. There's G of 5. So G of 5 is 3. So now we're going to come over here. If we have an input of 3, the output is 6. F of G of 5 is F of 3, which is 6. And that's it. Okay, I think that's where we're stopping for this video. And we'll pick it up with using the formulas.